So let's start by presenting a short historical overview of silicons and the fundamental working principles behind. Particularly, I will talk about the difference with graphite-based anodes and silicons. Then we will move into talking about silicon materials and some manufacturing considerations. So we'll summarize the different types of silicons that can be produced and the different pros and cons of all of them. Then we will briefly discuss our view, my take on the future of silicon anodes, and we will conclude with some takeaway and conclusions. To start the webinar, we have prepared a series of questions in the form of a live poll. So I encourage you to respond and participate to the live poll. The first question of today, did you know that silicon can be used as an anode material in lithium-ion batteries? Very generic question, just to get an understanding about the audience today. With 4 responses, not really, it is a new concept for me. Yes, I have heard about it before. I have some background knowledge, but not in depth, and certainly I have prior experience with working with silicon anodes of various forms. It can be pure silicon, silicon composites, or others. Great, thanks for the responses. Then let's go into explaining and discussing about silicon. Silicon has certainly emerged as very promising anode material in lithium-ion batteries for several decades, and it has been investigated widely and patented, of course, as well. Why silicon is so attractive? Well, one of the reasons is that it's low cost, and another reason is that it's greatly abundant. Silicon represents the second most abundant element in the Earth crust, and is also quite geographically spread. However, still China is dominating the supply and covers up to 3/4 of the global total production. Also, the cost of silicon raw material is very competitive and in some cases even cheaper when you compare it with the cost of battery-grade materials. Now let's look at a brief overview of publications covering silicon anode materials in academic publications. So up to now, we can see that there are 4,000 publications, and it has been growing exponentially since the last 2 decades. In comparison with the number of publications that cover lithium-ion batteries as a whole, we can also see that the interest has increased. So if we look at the beginning of 2000, the years 2000, the ratio between silicon lithium-ion batteries and lithium-ion batteries in general was around 13–14%, and that has increased to almost 20% in the last few years. Certainly, the patent landscape is also very interesting to look at. There are many big players in the field that have an extensive and very impressive patent portfolio on silicon, and not only silicon production, but components that are needed to work with silicon, binders, electrolytes, and so on. I will not spend a lot of time on the early publications, but maybe highlight some key findings that helped improving the performance of silicon through the last 2 decades, particularly. We can look at the first publications in which silicon alloy materials were used in lithium-ion batteries, and these date from back the 60s and the 70s. It is also worth mentioning that in the early 2000s, there was the first publications with fluorinated compounds that can be used as additives in the electrolyte. So FEC is widely used and reported as state-of-the-art electrolyte or co-solvent, that can make silicon anodes work. Also, of course, there are multiple works that have been published around the development of new binders that are able to accommodate the expansion of the silicon material. And of course, in the area of electrolyte, there are a lot of publications looking at the SEI layer that is built up in silicon materials, and how having inorganic rich SEI layers are favorable compared to organic SEI layers. In terms of silicon types, we can have publications and find publications that showcase multiple forms in the nano size all the way up to micro size, nanowires, nanotrees, or other types of material. And in the field of commercialization, of course, silicon has already made it into the market, into commercial products. initially with small amounts in the formulation, like those that you can find with silicon oxides or silicon suboxides in small quantities, maybe 1-3 weight% in the anode formulation, all the way up to possibilities in which you have 100% silicon material. For example, in the case of Amprius, is where you have this type of materials. But let's look at really the main reason to consider silicon as an anode material for lithium-ion batteries. And this is coming from its intrinsic specific capacity, which is quite impressive. Silicon can deliver up to 10 times more capacity than conventional graphite anode materials, with an outstanding theoretical capacity of more than 3,500 milliampere-hour gram compared to 372 milliampere-hour gram in graphite. In terms of volume, there is a threefold increase in volumetric capacity due to the fact that silicon expands considerably more than graphite. As opposed to graphite, that can only accommodate 1 atom of lithium per 6 atoms of carbon, in the case of silicon, only 1 atom of silicon can hold almost 4 atoms of lithium, owing to the formation of this metastable crystalline phase, lithium-15, silicon-4. Another difference is the respective working principles. Of course, I will explain shortly after what I mean by this, but in the case of graphite, the lithium intercalates in the graphitic structure, whereas in the case of silicon, the lithium and the silicon alloys during the charge and discharge process. The current battery technology, of course, you are very well aware that is greatly dominated by graphite anodes, in which you mix graphite powder with some binders, some small amount of carbon additives to produce the anode. And this is done at large scale, of course, in many of the applications that we use in our daily lives. Early developments transition to incorporating small amounts of silicon, typically silicon oxides, in the range of 2-5 weight%, and they act as additive in the anode formulation. Still, graphite is the majority of the active material. In the last decade, there has been a clear trend to increase the amount of silicon more and more, reaching a mid-silicon regime in which we can see materials that have around 20-30% weight of silicon in the formulation, the rest still being graphite and some binder material. Of course, the ultimate scenario is when we can replace graphite completely by silicon anode, making it the only active material in the formulation. And of course, this allows for an impressive increase of energy density of up to 40%. Now let's look at the fundamentals of both materials, graphite and silicon, and try to present differences between both of them. As mentioned before, and you are very well aware, lithium intercalates into the graphitic structure and causes the graphene-like layers to expand. Here I present the voltage profile in which you see the different stages in which the lithium intercalates in the graphite, and this has been widely explained and understood in literature and research. At the point where the graphite reaches maximum capacity, this 372 milliampere-hour gram, the material will expand around 10-13% in volume. In the case of silicon material, the uptake of lithium occurs via an alloying process. First, we will build the SEI layer, which occurs in this voltage profile around 0.8 volts, and the further uptake of lithium goes into an amorphization of the material, forming these lithium silicon compounds of amorphous nature. Upon further lithiation, there is a crystallization in which we reach the lithium-15 silicon-4 form, which is the highest lithiated phase, which can be obtained at room temperature. Of course, one thing to notice, and we can see it clearly in these voltage profiles, is that in general terms, the silicon anodes will have a lower Coulombic efficiency, as depicted by the fact that the lithiation capacity is considerably higher than the delithiation capacity. Here I present an illustration of these structural changes that I've mentioned before and that occur when we start by having a crystalline silicon material. When we fully lithiate the material, we form this crystalline phase, lithium-15 silicon-4. And this is accompanied by a great expansion of the material. This structure has been described as the closest packing of two types of atoms of different sizes. all the silicon atoms are isolated and are in equivalent coordination size, coordinated by 12 lithium atoms. The insertion of lithium, therefore, results in the total destruction of the silicon-silicon bonds and a massive increase of the volume. Upon dilithiation, the anamorphous phase is formed, and this occurs irreversibly. So we go through an expansion and a contraction of the material. When charging and discharging the battery, we follow the path below, so we never recover the original crystalline phase of the silicon. As a result of these massive changes in volume, this expansion and this contraction of the silicon will make the particles to suffer, mechanically speaking, quite a lot, even leading to swelling, breaking of the particles, or even pulverization. When forming the SEI layer, this expansion and contraction will make that the SEI layer breaks, leaving more areas of the silicon for further degradation. This leads to secondary buildup of SEI layer and effectively at some point even consumption of the electrolyte. Ultimately, of course, the binder is not able to hold the particles together anymore. You lose cohesion of the electrode and problems of addition even with the copper in extreme cases. Summarizing briefly the pros and the cons of silicon versus graphite materials, let's look at this very briefly. So, of course, we have mentioned silicon has a higher intrinsic capacity. It is abundant and cost-effective, particularly when we look at the cost per capacity or watt hour, for example, per kilogram. There is a reduced risk of lithium plating. I didn't explain per se this concept, but because the silicon is working at a higher operating voltage, we reduce the risk of lithium plating that takes place with graphite, for example, at fast operations and low temperatures. Silicon offers great flexibility in the design. We have different types of silicon materials. I will explain briefly about this in a few slides. And one of the big advantages is that in some silicon types of materials, we have drop-in solutions. So we can just replace the graphite by silicon in a very smooth way. Negative points, as mentioned, of course, the expansion and the contraction. The SEI layer is not so stable as with graphite materials, and in some cases, even there is an electrolyte dry out of the system. In some cases, of course, you need to develop or adapt binders and electrolytes to work with silicon. Not necessarily the solutions that work with graphite can be transferred to silicon. And for some types of silicon materials, not all the fabrication techniques are transferable. Some adaptation might be required. So these are some of the things that we can summarize up to now. Now let's move into different types of silicon materials and some of the manufacturing considerations that we have to have in mind when producing this. And we move into the second poll of today. How many types do you think there are of silicon-based materials that are currently being used in lithium-ion battery technologies? Lithium battery anodes. So just giving you a few options for this question. So there is no right or wrong answer actually, because there are many ways to classify silicon materials, and we have taken a very simplified approach for this presentation. But yeah, good. Great. Thanks for the responses, and let's move on into presenting the materials in which we can find silicon in the anode. We have here three types of silicon materials, and we start by silicon oxide, silicon suboxide materials. Actually, these are the ones that were firstly demonstrated in lithium-ion batteries in the early 90s, actually, so already quite some time ago. The production is quite simple in this type of materials and is not that costly. So silicon oxides is a compound that has been known since early 19th century actually, and the production is it's rather simple. It goes through the thermal evaporation of the compounds, the silicon and the silicon oxide, and a rapid quenching of the resulting vapors. In this case, we find typically small amounts in the anode formulation, so maybe even up to 10 weight percent can be seen in some cases, but not more than that typically. And therefore the gains in capacity are also moderate. The expansion is also much reduced compared to other silicon types. Then the second type of material is the silicon carbon structures. In this case, we have a silicon material that can be, for example, nano size and embedded in certain types of carbon structures. And these carbon structures can be of various different origins, cellulose-based, graphitic in nature. When talking about silicon carbon materials, we typically consider the deposition of silicon via the silent route. This is what comes to mind more typically. And having this carbon coverage around the silicon material offers great protection versus the electrolyte degradation. So there is a clearly advantage of using these materials. But of course, you have to mix the two components, and this has certain manufacturing considerations. In the last case, we present pure silicon alternatives, and these can also be found in various forms from nano to micro-sized structures. You can also engineer or create a certain type of porosity within the particles. For example, this is the route that E-magy takes in developing our anode material. And in a very simplified way, we have two routes to produce pure silicon materials. We have the silent route and the metallurgical route. In both cases, you have pros and cons, and there will be webinars later on down the road that will go deeper into explaining these two different routes. Now I will try to, out of these types of pure silicon materials, I will try to explain some manufacturing considerations or some aspects that are not so widely known and could be interesting to have a look at them and spend some time discussing them. So when we look at the material produced by the silent route via CVD process, we have these nanostructures that grow in the copper. So the copper acts as a catalyst actually, and you can grow in this copper different types of structures, nano wires or nano trees and so on. In this case, you have to couple the anode production really to the silane production facility, because silane is a gas that you cannot so easily transport and handle. There are a lot of associated risk, health and environmental risks when handling silane. So this is a point of attention when producing silane derived anodes. Of course, you have a limit as well into how much you can grow the silicon structure. There's a limitation in the thickness or the loading, the active loading of silicon material in the anode. So this can be considered as a drawback. And because the addition between the silicon material and the copper is so strong, the expansion and contraction that takes place during operation can even lead to some copper wrinkling. And these effects can also be visible when, for example, doing prelithiation on this type of materials. For certain types of anode materials, it is critical as well to have a good contact point with the current collector. And when you are growing silicon onto the copper, there can be issues in the welding process. So cleaning the tap area is not so easy as with other slurry type formulations. So this is another point of attention when using these materials. And then I will present the case of using powder-like materials, like for example, E-magy powder, silicon powder material. In this case, we have to proceed in producing a slurry, which is very similar to what we produce in a graphite anode. So we have to mix the active material with a carbon additive and a binder. So this is considered a drop-in solution. Also, it's compatible with water-based formulation, so this is very nice to handle. Let's say there are not so many difficulties when like handling NMP or otherwise. But of course, one thing that you have to consider is that silicon under certain pH in the slurry media will generate hydrogen. So the video was activated a bit earlier than I wanted it, but under certain pH conditions, there is hydrogen being generated in the slurry, and certainly you want to avoid this in a pilot line when you are producing liters and liters of slurry. So you have to be very careful in adjusting the pH of your media very carefully. So as mentioned, this process is compatible with existing pilot lines, so the roll-to-roll process is smooth to take place. And I will only mention a couple of points of attention. For example, the calendaring process might be critical with this type of materials. Of course, silicon is of a brittle nature, so when you apply the pressures that are associated with calendaring, you might even break particles, silicon particles, or you might even pierce the copper foil in some extreme cases. And of course, you are all very well aware that the industry is moving into processes that are solvent-free. There are a lot of efforts towards dry extrusion, and the behavior or the way the silicon particles behave during this process is very different compared to graphite, which is acting typically as a lubricant during the process. So these are some of the considerations you have to take in mind when producing silicon anodes of this type. Now let's mention very briefly a bit some points regarding the future of silicon anodes or my view on it. Not before presenting the last poll question of today. So which one is, in your opinion, the technology that will dominate the market in the next 10 years? 10 years, let's put this time frame. So of course there is a lot of interest in solid state with lithium metal, but why not solid state with silicon-based anodes? That's also a possibility that I will present. Or maybe the traditional lithium-ion batteries with still liquid electrolytes, but maybe advanced in some way, or advanced in the way of introducing silicon anodes of different types or at different ratios. And the last response, more looking at the post-lithium technologies, maybe in the next 10 years is a bit too early for them to enter into the market. But yeah, what do you think? Okay, so very split decisions in the audience. We are not that many in the afternoon. We were very busy in the morning, so here the ratios are very balanced. Good, thanks for that. So now, very briefly, let's look at the future or how the future of silicon might look. And this is a very simplified way to present the different silicon type materials that I presented before. Here we are looking at the cost of production versus the energy density that you can achieve with this type of materials. And of course, you could look at other properties like cyclability or power capabilities or so on. In the scenario having low cost and low energy possibilities, we have the material presented before with small amounts of silicon oxide in the formulation. They have been used in the past. They have been reaching the market even in various applications, but we consider them more a type of technology that will phase out eventually because the gains in energy density are really moderate. Then we are looking at the mid-range silicon composites, and we have seen a great increase in interest in the last few years in this range. We have materials having silicon in around 30% of weight, for example, and then you gain in energy density, but of course you increase the cost of investment. The capex goes up. You are producing a more complex material, and that leads to more cost in the production. And for what we can see for the future and the near-term future is that these two technologies, looking at high silicon anodes and 100% silicon anodes, will share somehow a piece of the market, and they will have to adapt to different customer needs. And ultimately, this will be a balance between the cost of production and the gains in energy density. So, for example, the route followed by E-magy, looking at the metallurgical grade silicon, it's what we consider low cost, low capex. We use metallurgical grade silicon, which is rather cheap, but it gives you considerable gains in energy density. And then when we look at the CVD phase, the CVD route, the silent route, you have high capex and high investments. Of course, you can also gain quite a bit in energy density. So it's a bit a balance between these properties. And as mentioned before, just to touch upon the topic of solid state, it is clear that silicon offers a very realistic competition towards lithium metal. Lithium metal also expands and contracts during operation. It's something that the people typically don't discuss that much, but silicon expands, also lithium expands during operation. And we can see that there has been a great increase in the interest, not only in the publications, but in the patent landscape when using silicon materials in solid state applications. One of the biggest advantages, of course, is that silicon is much more easy to handle. The dry room requirements are not so harsh as with handling lithium. The operation is much safer as well. There are no risk of dendrites forming. So there are certain aspects that the silicon can cover really well. And of course, there has been many publications demonstrating compatibility with various types of solid electrolyte chemistries, from the sulfides or polymer based. It has been demonstrated that silicon can work in these scenarios. And of course, there are challenges in scale up production, challenges of the, for example, pressure needed for testing some of these solutions. But we can clearly see that the future of solid state batteries is linked very closely with silicon materials. Now I will move into the conclusions. We have presented silicon as a viable anode material, an alternative to graphite, which is dominating the market up to now. There are efforts towards minimizing all the drawbacks that I presented before, and these efforts are in the right direction and will enable widespread commercialization in the years to come. We have seen, and there are many types of silicon materials that make it a very ideal anode candidate because it offers a lot of flexibility that you don't have with graphite-like materials, and it's very versatile. It will allow energy density that is required for certain applications in the market as of today.